Hi everybody, thank you for coming to my presentation. My name is Jeff Taylor. I'm a PhD candidate at Utah State University, and I'm glad you're here. And I hope that you'll enjoy this presentation. I'm going to be talking about a study that I did on comparing theoretical and high-fidelity aerostructural solutions. So this is part of a body of work that I've been doing at Utah State University with Dr. Douglas Hunsaker regarding the development of analytic solutions and theories for aerostructural optimization. And so what we wanted to do with this study was to compare our analytic solutions as well as some other analytic solutions to high-fidelity solutions and see how well they match. So just a quick background of what we're trying to do here. So a lot of us are familiar with the elliptic lift distribution. And the elliptic lift distribution has been shown to be optimal for minimizing drag on wings with fixed weight and wingspan. It's an aerodynamic optimum solution. So the induced drag from lifting line theory is shown here at the top left. And we can see that from this equation, the induced drag is a function of the weight, which is W, the wingspan, which is B, and the lift distribution, which is defined using these normalized Fourier coefficients B sub n. Now, if weight and wingspan are fixed, then induced drag is minimized by setting all of the Bn coefficients to 0. However, if weight and wingspan are allowed to change, there's a trade-off that develops between wingspan and lift distribution and weight. And it's really based on the bending moments. As we increase the wingspan, or as we change the lift distribution, we change the bending moments on the wing, and so therefore we change the amount of weight required to support those bending moments. So theoretically, we can show from lifting line theory that minimizing induced drag, if weight and wingspan are allowed to vary, often results in a solution that has a non-elliptic lift distribution. So in other words, the optimum lift distribution under structural constraints is non-elliptic. So the plot here on the right shows the results from a study done by Prandtl in 1933, in which he explored this trade-off and found that there was a bell-shaped lift distribution that minimized induced drag, and it produced 11.1% less induced drag than the elliptic lift distribution, because it allowed a wingspan increase of 22.5% over that allowed by the elliptic lift distribution with no increase in wing structure weight. So there's a whole body of high-fidelity aerodynamic and aerostructural literature out there, and in fact that's where things are really headed. So the elliptic lift distribution is very appropriately used as a benchmark in aerodynamic studies. So what's shown here on the left is a aerodynamic shape optimization study out of the University of Michigan. And you can see on the bottom, although it's kind of thin, you can see that the optimized solution, the one on the right, has a lift distribution that's very nearly elliptic. And so we see that the elliptic lift distribution is optimal for this case, which is an aerodynamic optimization study. Now the figure shown here on the right is an aerostructural optimization study out from the same group at the University of Michigan. And here now you can see from the solution on the bottom that the optimum lift distribution for cruise, which is the solid blue line, is non-elliptic because there's an aerostructural trade-off going on. And so, but the elliptic lift distribution is still shown here as a reference. So the question that we had was, well, why don't we use some aerostructural solutions as benchmarks? We have these theoretical aerostructural solutions, why don't we use them? And so some of the solutions that we've had, we developed in the past couple of years, are shown here. So they're kind of grouped into three categories. The plot on the left shows two optimum lift distributions that are, of course, as you can see, non-elliptic for wings with constraints of maximum stress, maximum deflection, fixed payload weight or fixed weight of all non-structural components in the wing, and fixed wing loading, which keeps the wing loading, which keeps the performance of the wing similar between the baseline and the optimized design. The results in the center here are for a very similar study where instead of using a fixed wing loading constraint, we used a fixed stall speed constraint. So with the same purpose, we wanted to keep performance fairly similar between baseline and optimized wings. And then the figure shown here on the right is an extension of these studies to tapered wings. And we found actually that taper doesn't really significantly affect the optimum lift distribution. So we wanted to compare these to one another and against these high fidelity solutions. And in order to compare lift distributions against one another, it's helpful to normalize them so that we can put them on the same scale. And that way we can kind of see how much they vary. And so shown here at the bottom is each one of these lift distributions plotted against one another on this normalized scale. And you can see that there's a wide variety that ranges between elliptic and bell-shaped. So the groups that we used for this study were based on the theoretical solutions that were available, and we broke up all of our comparisons into either studies with integrated bending moment constraints, studies with root bending moment constraints, or studies that have constraints on the stress or the deflection combined with performance-related constraints, either related to the wing loading or to stall. And today I just want to show results from 2 of these studies. And you can see on the right here, I've broken out which studies we're going to consider from each group. So first we'll look at studies that have integrated bending moment constraints. And our baseline analytic solution in this category is Prandtl 1933 solution. And it's highlighted here in yellow on the right. Now on the left, I've shown the different wing configurations that were used in some of these studies. So Prandtl's study used a rectangular wing. It assumed a rectangular wing. However, the studies in reference 44 and reference 45, which are both high-fidelity studies, used wings more representative of commercial aircraft. And so you can see, going back to the right to this plot, our high-fidelity studies are shown with triangles for reference 44 and circles for reference 45. The solution from reference 44 matches Prandtl's solution very well. And the solution from reference 45 also follows the same trend, but you can see there's kind of waviness in it. Well, it turns out that the authors of reference 45 controlled the lift distribution using the twist at only 3 locations on the wing. So this waviness that we see is not unexpected, and in fact, it corresponds. If we were to make the resolution a lot higher with our twist, then we would be able to match Prandtl's lift distribution, and that's where the solution would tend. So I want to now consider the stress-limited design with fixed wing loading. So this is kind of like the golden child result in our paper. So shown here at the right, you can see the red lift distribution is our baseline analytic solution. It comes from a study that we did last year. And you can see that it agrees very well with a whole lot of other studies. And all of the ones that are marked with symbols are high fidelity or computational studies, and 4 of them are high fidelity studies. Shown at the left are the different wing configurations, just to kind of give an idea of the diversity that we've got here. So we were actually pretty surprised by this result, but very pleased, because we can see that there's really good agreement between the studies here under these constraints. And part of this, I think, is because the constraints in high-fidelity studies are best matched, the constraints that we used in our analytics study, there's lots of high-fidelity studies that have constraints that are very similar or comparable. So just to bring it home, high-fidelity solutions in general match the theoretical aerostructural solutions that we looked at in this paper pretty well. And it follows then that the analytic solutions are appropriately used as benchmarks in high-fidelity studies. But we don't see that very often. So what we really wanted to do here is kind of promote the idea of using theoretical aerostructural studies as benchmarks in high-fidelity solutions, instead of just using the elliptic lift distribution. Because in fact, the elliptic lift distribution, the constraints don't match our aerostructural studies very well. So kind of to hit it home, we have a final comparison of one of the solutions from our paper, this analytic solution shown in green, compared to a study by Kinway et al. At the University of Michigan with very similar constraints. And you can see that the green optimum theoretical solution matches the blue optimum cruise lift distribution from the high-fidelity study really pretty well. So I invite you to look at the paper. There's a lot more of this analysis, including an analysis looking at a comparison of wingspan and drag values from these solutions as well. So hope you enjoyed the presentation. If you have any questions that you're not able to ask, you can email them to me at the email shown here. So thank you very much.